Hi everyone, this is Professor Lucas, and in this video we'll be covering cryptography basics. We'll look at exactly how cryptography plays into the CIA triangle in cybersecurity that we've covered many times in our cybersecurity courses. We'll also look at some fun examples using emojis, and then we'll actually look at how a cipher wheel works to encrypt and decrypt messages. First, again, we've covered the CIA triangle many times in your cybersecurity courses. Remember, that stands for confidentiality, integrity, and availability. Now, cryptography can be applied at pretty much each one of these layers, or to achieve each one of these pillars of the CIA triangle. When we think about confidentiality, remember that is us trying to prove we are who we are, right? Who we say we are, who we claim to be. Here with cryptography, you can hide or scramble data so only the intended recipient can access it. This can be done via encryption. There are many encryption algorithms out there. New ones are being developed all the time because, again, when an encryption algorithm is out in the market for a very long time, people are always trying to actually crack it. Some examples of different encryption algorithms are AES, DES. Those are more symmetric algorithms. 3DES. Symmetric algorithms are not used as much. We usually use asymmetric algorithms, which are more like public key encryption because they're a little more secure. They don't use the same keys on both sides of the encryption. And those are like RSA, the Diffie-Hellman, and there's a lot of other ones on the market. So again, they're always trying to create new ones. So the goal of encryption is to apply some type of formula, usually a very complex mathematical formula, to a plain text or clear text that is not encrypted. Basically, anyone can read it, and make it to where it is unreadable after you apply that algorithm or that encryption, right? So the output is called ciphertext. We're going to get some hands-on experience doing that in a minute. Integrity, remember, integrity is the content has not been changed. So think about in a safe. If I put something in a safe, when I go back and get it, I want that contents of that safe, no matter what it is, to be unchanged, right? Cryptography can verify the data integrity, making sure that nothing has been altered. For example, there are these things called hash functions. Every file has one. So if you actually note what the hash function is on one end, if you send it to somebody else, that hash function should still be the same on the other end. If there are any changes to that file, like if somebody does a man-in-the-middle attack and somebody captures that file, makes some changes to it, and then try to present it to you as a legitimate unchanged file, the hash outcome should be different because there were some changes, therefore, cluing you in that something has happened, possibly fraudulent. And then finally, availability. Now, availability really doesn't have to do too much with actual cybersecurity in terms of like making sure it's safe, but availability is important because, again, most companies shoot for like the 5 nines or even now the 6 nines, meaning up 99.9999% of the time. So with high availability, the goal is to be up and available as much as possible. So if you are a major company like Amazon, who does a lot of online retailing, you need to be up as much as possible. Doesn't sound like a huge difference, but if you were up 99% of the time, sounds good, but that means you'd actually be down about 3.5 days over the course of a year. Now, a company like Amazon that makes hundreds of thousands of dollars per minute, 3.5 days is a lot of lost revenue, right? When you multiply that out. Now, if you're up 99.9999% of the time, guess what? That 3.5 days of downtime decreases to like 3.5 minutes per year. So you can see the big difference there. Now, for availability, cryptography can ensure uninterrupted data access. So this could include maintaining hardware, making regular upgrades, having a plan for failover. So again, it does affect all three of the different layers. Now here on the screen, you'll see many forms of cryptography over the years. Cryptography is nothing new. It's technically been going on for a really long time, thousands of years, in fact. So at the upper left-hand corner, you'll see something called a tally. This was a very ancient method of encrypting a secret message. So back then in like the Julius Caesar days, some people even call this a Caesar cipher. So they would actually take a really large piece of sheepskin, write letters on it in their language, and then they would cut it into strips, right? They would write the message on it. They would cut it into strips, wrap it around a pole, and then that walking stick or that pole would have to be wrapped in a very specific way for the message to appear. Now, if the messenger was caught on like the battlefield, if they were transporting a secret message and the enemy captured them, they wouldn't know what it was, because they would have to know exactly how to wrap that pole with those letters for them to align correctly. Right? In the upper right hand corner, you see a kind of an upgraded version of this. And these are, if you ever watch those Da Vinci Code movies and things like that. So this is a more of a rotating wheel that has many, many combinations. And sometimes in the middle, they would even have a glass jar of like vinegar that would ruin everything if you accidentally did it wrong, right? So, and tried to actually decode it. So it was very important to get it right. In the bottom left-hand corner, you see something that was used in World War II called the Enigma machine. So what Germany did was they encoded lots of messages to be sent across the battlefield. Now, we could not crack this for a very long time. However, the United States and other countries got together and they actually were able to crack this and able to intercept all and read all of the messages that Germany was sending across the battlefield. So it really turned the tide of World War II. The bottom right-hand corner is a simple substitution cipher. So this was one where computing was starting to get involved, where you just basically substitute one letter for the other. This is called rotation 13 or substitution 13. So basically an A would become an N, or vice versa. A B would become an O, a C would become a P, a D would become a Q, so on and so on. So, if you wrote the letter A in the plain text, your encrypted message would actually have an N instead of an A. So the encrypted message would actually be pretty much just, jumbled letters. It wouldn't make any sense to us in regular plain text English. Like you see the letter, the word hello down there, the H becomes U, the E becomes R, the L becomes Y, the L becomes Y again, and the O becomes B. So the encrypted message would be URYYB. That looks nothing like hello, right? Now, with that, you kind of see some patterns there too. The L's are always going to be a Y on rotation 13. Now, we'll see changing the rotation, how that works in a minute. And then in the middle there, you see like a complex mathematical algorithm or formula. Today, computers are much better than we are. If you notice, this would take us a long time. Computers can do it very quickly. Now, we're going to start with some fun. Let's do some emoji encryption, right? All of you know what emojis are. We use them all the time in text messages and, to be funny. So let's see if you can decrypt some of these encrypted messages that have been encrypted with emojis. Now, again, I'm going to give you the answer, but I'll give you a couple seconds and I'm going to pause on each slide. So if you don't hear anything, that's okay. I'll come back. I'll give you 5 seconds per slide. So what do you think this one is? Don't cry over spilled milk. Get it? All right, let's try some more. What about this one? Downtown. So it's the word town written in a down direction. All right, what about this one? The bee's knees. That's kind of an old saying. You may not have heard of that one, but it's kind of an older saying when something's really good. All right, what about this one? Third time's a charm. So you may have heard that, kind of a lucky statement. All right, more words here. What about this one? Crossroads. So you got the word roads 2 different times. Crossing. Crossroads. All right, what about this one? Read it and weep. So if you ever played cards and stuff, people lay their cards down and they won. Read it and weep. All right, this is kind of a long one here. Barking up the wrong tree. So it's kind of like a dog speaking up wrong tree. So barking up the wrong tree. Now, all of your English teachers are going to want to make sure you get this English rule correct. Don't know it? I before E except after C, right? And what about this one? Saving money for a rainy day. All right, so all those are pretty cool and fun to just kind of encrypt and decrypt some messages with some emojis. Now, in a more practical way, kind of like we did with the substitution cipher, we can do that with a cipher wheel. So a cipher wheel is a way for you to be able to rotate the middle, all right? The outside letters, okay, the very outer wheel, these are independent of each other, okay? So the outer wheel, where you see the larger letters, are regular plain text. That's your regular decrypted message. So if you want to say hello, then it would just be HELLO, right? The inner wheel and numbers go together. They turn together. Those are the encrypted letters, all right? Right now I've got it where it's just A is A, B is B, C is C. So there's no encryption going on. If you turn the middle though, all right, to rotation 13, which we were practicing a while ago with hello, the encrypted message was URYYB. So I'm going to use my mouse here, so follow it. So I have turned, if you go back one, remember the A and the 0, that means no encryption is happening, okay? Now I've got the A, the N, and 13, okay? You always want to look for right here for lining up with the big A. This is the regular plain text letter. What is this number right here? That will tell you the rotation. Always look for the A. It's like your North Star, your guiding light, okay? This is your starting place. So rotation 13, okay? So if I told you turn to rotation 13, you would line this up so you could figure out the encrypted message. So the inner circle here is our encrypted letters. So I'm going to go find, because I gave you the encrypted letters, I'm going to go find the U, all right? That is right here, okay? And I'm going to go up to H. So I know my first letter instead of U should be H. Then I'm going to go to R. I found the inner wheel R. Okay, remember these are the encrypted letters. And I'm going to go up to E. So far I have H, E. You can tell these two letters are the same. So I'm going to go to the middle again and find my Y. Okay, that's down here. And go up to L. So I got HELL. And then I've got B. So I'm going to go to the inner B. Okay, and then I'm going to go up to O. All right, so I get HELLO for hello. All right, let's try one more on rotation 13. So here I've got PLORE. So again, still on rotation 13. So I'm going to go to the inner wheel and find P, go up to C. So my first letter C. Then I'm going to go find L on the inner wheel. Again, that's the encrypted letters. Go up to Y. So I've got CY. I'm going to find O on the inner wheel. Go up to B. So CYB. I'm going to find R on my inner wheel right here. Go up to E. So I got CYBE. Think you know what it is? All right, let me find E on my inner wheel. And that's R. So CYBER. All right. Now, what if I rotate it? Now, don't worry about these lines. I did this as an image. Sometimes the lines don't quite line up. But again, I was rotating it digitally. But again, we want to find our big A, okay? And you see now that a 23 is below the big A and an X, okay? So this is rotation 23. It's not rotation 13 anymore. It's rotation 23. So the encrypted letters that I'm going to find and then go out to the plain text letters is going to be different, okay? So let me go find an E. So the encrypted E will go up to H this time, all right? Remember that was different last time, so an E goes up to H this time. Then I'm going to go find B, all right? I'm going to go up to E. I'm going to go find an I. That'll go up to L. You see there's two I's, so there's two L's. Think you know what this word is again? And then I'm going to find the encrypted inner wheel L and go up to O. So again, it's still hello. Now, if I go back a couple slides, before it was URYYB, but that was on rotation 13. This time on rotation 23 is EBIIL. So you notice it's different if I change the rotation, right? So same plain text message, but different encrypted message. So you can kind of keep the hackers on their toes a little bit. All right, now you can try creating your own. I'm going to include a link in here with the PowerPoint, and you can actually rotate the inner wheel in PowerPoint and kind of change it up, and you can practice encrypting and decrypting. I printed it out. If you print them out separately, you can even like put a little pin in the middle, and you can rotate the middle to create your own cipher wheel. Now, if your wheels are turning here, no pun intended. Get it? See what I did there? If your wheels are turning, cipher wheel. Again, I just put that together. Totally unintended, terrible joke. But as we continue, if you encrypt it, let's just say this on rotation 23, you encrypt it hello and it's EBIIL. What if you actually took the encrypted message and rotated the wheel again and encrypted the encrypted message? Right? Then you've doubled your level of encryption. So you would have to doubly decrypt it. I'd have to tell you, hey, I encrypted it on, let's say this time we do a rotation 16, right? So you'd have to unencrypt it or sorry, decrypt it using rotation 16 or whatever one you do, and then you have to decrypt it again using rotation 23 to get all the way back to hello. Now this is what actual computer algorithms do. They decrypt it over and over and over and over again to create a higher level of encryption. Now the only issue with encryption right now is computing power. Now quantum computing, if you ever heard of that, will help solve this issue and create greater issues. Quantum computing is very powerful computers that can run more calculations per second. Now, the more calculations and powerful your computer is, the higher level of encryption you can encrypt, but you can also decrypt. So from a safety security standpoint, think about if I created the most secure, hardest to crack algorithm, and it was a lot. So that increases the bits of encryption, we call it. If it was like, a million bits of encryption. Now, if your email were to use that encryption algorithm that was a million bits of encryption, it might take your your computer, a year to decrypt it to log in. That's not practical, right? That goes back to availability. So we have to have the right computing power, so you can't overdo the algorithm to where the computer can't actually encrypt and decrypt along with the algorithm. Now, quantum computing changes that because it allows us to encrypt faster and with greater level of encryption. However, hackers can also decrypt at a higher level, meaning they can try to hack and crack all these algorithms. So again, just a note, if you ever heard of quantum computing, that is a thing, kind of like AI is taking the cybersecurity world by storm right now. Now is quiz time. Let's put what we just learned into practice. There's a step 2 in Moodle in this module that tells you to complete a 5-question quiz called the Module 10 Multi-Step Quiz Cryptography Basics. Basically, you'll be decrypting already encrypted messages using a cipher wheel. The cipher wheel is already going to be in the question, rotate it to the correct rotation. Remember, you only have one attempt and there is a 30-minute time limit, so be ready to complete this all in one setting. I hope you had fun learning more about cryptography basics and hope you have fun decrypting some of the messages in our quiz.